Alright, so welcome back to the fourth part of the second week. In this video, we're going to have a quick discussion about how the exchange property of matroids is actually crucial to the correctness of the greedy approach when we are talking about our generic optimization problem. So let me introduce another term here, which is a subset system. So this is simply a finite collection of hereditary sets. So recall that heredity was the second property that we defined when we were talking about matroids. So just to recall what it means, we said that if X belongs to the family F and Y is a subset of X, then Y also belongs to F. This was heredity. So if you have a family F that is only guaranteed to satisfy heredity, but may or may not satisfy the exchange property, then it's called a subset system. So our claim is that if you have a subset system that does not satisfy the exchange property, so it's not a matroid, then you can actually come up with a collection of weights which will throw off the greedy algorithm. So you can design a weighting function which, if used by greedy, will mislead it. It will end up giving you suboptimal output. So let me make this claim explicit. Okay, so this is the claim that we are making here. If you have a family which is heredity but does not satisfy the exchange property, then we can come up with a weight function such that if you were to run the greedy algorithm on this family, it's going to return a set which is not the optimal choice. So let's try and design a weight function which achieves this. Feel free to pause here and puzzle it out yourself if you would like to. But what we are going to do is start with the assumption that F is not a matroid. So in particular, F fails to satisfy the exchange property. Now let's think carefully about what it means to fail the exchange property. The exchange property said that for any pair of sets X, Y in F, if the size of X is bigger than the size of Y, then there exists some element X in X minus Y such that Y union X belongs to F. Now, to fail this property would mean negating this statement. So let's carefully negate this statement. So what we have is that there is a pair of sets in the family such that X is bigger than Y, but it's not possible to pull in an element from X minus Y to extend Y and remain independent. So, but for every choice of X in X minus Y, the set Y union X is not in the family F. Please feel free to pause the video here and stare at this for a minute to convince yourself that this is indeed the negation of the property that is the exchange property. Because we are going to anchor our argument around this particular pair of sets X and Y. So basically, for the family to fail the exchange property means that there is a pair of sets which don't satisfy the exchange requirement, and not satisfying the exchange requirement basically means that we have this big set X and we have a set Y that is smaller than it, and basically no matter which element we pick in X minus Y, if we try to add it to Y, we move out of the independent set collection. Okay, so that's what it means for this family to violate the exchange property. Okay, so now we want to come up with a weight function that will actually mislead the greedy algorithm. We want it to make choices that are not optimal. So one thing that may be intuitive is that the set X is bigger than the set Y. So we might want to plan so that X is the optimal output, but Y is the greedy output. Okay, so this is what we will try and ensure. We will make the elements in Y look attractive to greedy, but what will happen is that once greedy has picked all the elements of Y, notice that it's blocked out from picking any elements from X, because any elements in X that remain, that is, because we know that the exchange property is being violated. So once you have picked all of Y, you cannot pick anything more from X, because we know that Y union any element in X minus Y is not an independent set. So greedy will get stuck with Y, but we know that the best outcome is actually X. So how do we set up the weights so that X is the heavier set, but Y has the heavier elements, right? That's a good puzzle. If you want, you can pause the video here and try to think about it for a bit yourself. But let me give you one way to do this. So let me use M to denote the size of Y. And let's give all the elements in Y a weight of M plus 2. And let's give all the elements in X minus Y a weight of M plus 1. Everything else outside of X and Y can have a weight of 0. Okay, I don't really care about these elements. Let's see why this is a clever idea and why this will work. Okay, so what will greedy do? The heaviest elements are the elements in Y, because they have a weight of M plus 2. So the greedy algorithm will first approach all the elements of Y and it will collect all of them. And so the output of greedy is going to be M plus 2 into M, which is M squared plus 2M. I hope that's clear. There are M elements, each of them have a weight of M plus 2. So the total weight of the set that's output by greedy is M squared plus 2M. Yes? Okay, but what is the weight of X? Well, we know that the size of X is strictly bigger than the size of Y, which is M, which means that the size of X is at least M plus 1. It has at least M plus 1 elements, and each of these elements have a weight of at least M plus 1. Some of them are common to Y, so they may even have a weight of M plus 2. But in the worst case, X and Y may be completely disjoint sets. But still, the weight of X is guaranteed to be at least M plus 1 squared, because there are at least M plus 1 elements, and all elements have a weight of at least M plus 1. But M plus 1 squared is M squared plus 2M plus 1, which means that it's strictly bigger than what we have here. So we have achieved exactly what we set out to achieve, meaning that 1, we made all the elements in Y look attractive to greedy, but 2, we also managed to ensure that X is actually the bigger set. So greedy is misguided and will end up picking the wrong set. This is also what happened in the example that we saw right in the beginning. If you remember, we had this set, we had this element W, which had a weight of 50, and greedy just went after it, but after it picked W, it couldn't pick anything else. So that's the same phenomenon here, but we have abstracted it out to any setting for any family that does not satisfy the exchange property. So it's a more general result in that sense. Let's go back for a minute to the class scheduling problem that we have seen earlier. Remember, we had a bunch of time intervals and we were trying to figure out what's the largest collection of non-overlapping classes that we can pick. And we had this nice greedy algorithm which said, well, let's pick the class that ends first and go from there. Notice that if you just think about collections of non-overlapping classes, they don't actually form a matroid in the sense that they may violate the exchange axiom. Think about why that's true. You can have a larger collection of independent classes from where you cannot pull in anything into a smaller collection. It's similar to the kind of example that we had for the matching. So for example, you could have these two classes that are non-overlapping, and then you could have a third class which is overlapping with both of them, and you can think of this as your choice of y, and you can think of these two classes as being your set x, right? So notice that x is bigger than y, but you cannot extend y with either of the classes from x, right? So the concept of collections of non-overlapping classes, that's a family of things that does not satisfy the exchange axiom. But you might say, well, we just showed that if something does not satisfy the exchange axiom, then greedy doesn't work. But last week we just saw that greedy works. So what's going on? Well, the thing is that what we just showed is that if you don't satisfy the exchange property, then I can come up with a weighting scheme which makes greedy fail. So for example, I could associate a value with each of these classes, and in fact let's do that right now based on the proof that we just saw. So y is a collection of one class, so the size of y is 1, and x is 2 here. So let's assign some weights. Let's say that this green class here has a value of 3, whereas the two red classes have a value of 2 each, right? Now, if you were doing greedy in terms of picking the heaviest or the most valuable class first, then you're going to fail because you will go and pick this class. It'll give you a total value of 3, but the best thing to do was to actually pick the other two classes which gives you a total value of 4 for taking up two classes. If we look at the greedy approach that we tried last week, which was to pick the class that ends first. Now, remember there we were just trying to maximize the number of classes that we could take. We didn't have any concept of value. All the classes were equally valuable to us. We just wanted to maximize the total number of classes that we enroll for. But once classes have value, note that it can be immediately a bad strategy to pick the class that ends first, because this could be a very low value class compared to the other one that's overlapping with it. So this is an example with just two classes where the greedy algorithm is already doing badly. But this is happening only because now weights have entered the picture. The algorithm that we did last time was for a very special collection of weights, which is a uniform weighting scheme. All classes had the same weight. You can think of that common weight as being 1 or 10 or whatever, but the point is that all the classes had exactly the same weight, and that's why you got away with greedy. But what we are saying now is that if you are allowed to have weights, and what you're looking for is a maximal collection of mutually non-overlapping classes which have the largest weight, then greedy could land you in trouble. So you could do the earliest finish first, or you could simply do pick the most valuable class first. Both of these approaches, as you can see, run into problems because of the counter examples you see on the slide. So I hope that that was clear, and I hope that you're convinced that the exchange property is really crucial to the correctness of the greedy approach for our generic optimization problem. So that brings us to the end of this discussion. Next time we are going to introduce the problem of scheduling with deadlines, and we'll solve that by basically outsourcing it to the result that we proved last time, which is that greedy always works for a Matroid structure. So see you then.